I want to talk about finite order digital filters in terms of we call it status-based representation. Any finite order digital LTI filter, which could be used for power spectral representation, has a state space equation like that. So Z here is a vector, A is a matrix, B is a matrix, X is the input random vector, and Z is the output state. And A and B are two matrices. And the output, so this is state. So this is a state space representation of finite order digital LTI system. And of course, because A, B, C, and D are fixed in time, they are time invariant, and because both of these equations are linear, we call it linear time invariant system. So any linear time invariant system which could be represented, so here the input is X of K, is the input random process, and the final output is Y of K, and this is the system. But inside this system you have ZK, which is the state of the system, and this state is fed back in there. So there is one memory unit, so it's a memory, and the output of this memory is kept here. So this is ZK plus 1, and this is memory is a delay. So, and then here is ZK. So you keep it for the next iteration, and then in each iteration. So how many memories here, or the length of this memory, or length of ZK, is called the order of the system. So how many memory units you need in order to implement this difference equation, linear equation. So A is called transition matrix, and Y is the output. So the system could be written as this block diagram, because input is first multiplied by B. The input is also multiplied by D. So if you add the input to A times ZK, so you add it to the A times K, you calculate the state, you put a delay unit. So this is an array of delay units. So because this is a vector, and then this is used to calculate the output, because you get it multiplied by C and then calculate the output here. But also you multiply it by A to calculate the next state. Okay, so this is this is the state, and is not necessarily and this is the output. So usually you see input output, and sometimes you don't see the state. But in some cases, using the input and output, you may be able to calculate the state. In some cases, you may not be able to calculate. If you are able to calculate the state, we call it the system as observable. If not, it's not. So the stability of this system implies that the eigenvalue of all eigenvalues of this matrix, okay, they shall be all inside the unit circle. In other words, eigenvalues of this matrix A here, they are poles of your system. And the transfer function between input here, so you could say that x of n goes to h of z, which is like multiple input, multiple output. This h of z has this transfer function. And you see that why the eigenvalues of these ones. So if you put Zin minus I equal to 0, so you get the eigenvalues of A. And this gives you, if you write this is a matrix, but these entries of this matrix are like rational functions, then you can write it to the impulse response matrix.